memory. So as you know, virtual memory is imaginary memory. It does not exist. Okay. So in this memory, we assume the illusion is that the whole program, how many ever pages are there for the program or how many ever big the program is continuously stored from the address 0 to whatever the length of program is. Okay, whatever length of program is. So the program is assumed to be continuously stored in virtual memory. Or I can say that the content of secondary memory, if there are files, there is a file in secondary memory, this file from having the 1232 bytes size of this file is. Okay, so here in secondary memory, we assume we know that the program is present fully and it is continuously stored. So the same continuous illusion is there in the virtual memory also. Okay, so virtual memory is imaginary memory. Why it is required? What is the benefit of assuming this particular memory is, you know that RAM space is limited. Okay, RAM space is limited, and in this limited space, how many ever programs you are able to put for execution, okay, that many programs can run parallelly. Fine. Now, what I mean to say is, if there are only two programs, space for storing only two programs, okay, so there is the audio file which is running, or there is a Word file which is opened. Okay, so there are only two programs, and only these two programs can be there, can execute, or can be present in the system at a time. Okay, so only these two programs are executing at a time. So how many of our programs we are able to store, and that is called as the degree of multi-programming, the number of programs that can be executed at a time. Okay, that depends on how many programs code is present in memory at a time. Okay, so at a time, how many programs are there? Now here, in as per this, there are 4 programs at a time, means parallelly 4 programs are able to execute in the processor. Okay, now P1 program, suppose it is of 1000 bytes. Okay, totally P1 program is of 1000 bytes. P2 program is of 500 bytes. Okay, but the primary memory, suppose it is only 512 bytes. Okay, primary memory is only 512 bytes. Then this 1000 bytes cannot be stored together, and hence we store only the part of program which is required. Okay, so the, as you know, according to the paging concept, P1 program is divided into number of pages, and only the required page is stored into the memory. Okay, only the required pages of the programs are stored into the memory. Okay, and those pages are executed. Now there are 4 programs, so each programs, suppose the page size is 16 bytes is the page size. Okay, so few pages of each program are present in the memory. Fine. 16 bytes means how many frames are there? Totally it is of 512 bytes. Each page is 16 bytes. So 512 divided by 16, whatever you get, that many frames are there in the physical memory. Okay, what is 512 divided by 16?
32, ma'am.
Yeah, 32 frames are there in the physical memory. Okay, and 32 pages of any of these programs can be stored in the primary memory. Okay, so even though P1 is of 1000 bytes, okay, or and P3 is of suppose 1232 bytes. Okay, even though the P3, when it is executing, the complete program is of this many bytes. Okay, and many pages are required for it. So the complete program is not stored in physical memory at a time. Okay, only the required pages are stored, and this is beneficial. This is present because the CPU is, we are able to do such a technique of storing only few pages because PCU is assuming that there is the complete program is stored continuously in virtual memory, and hence CPU is generating addresses to this virtual memory. Okay, and that's why you are able to store only the required pages. Okay, however, whichever page CPU wants, it is referring. If that page is not there, the arrangement is done such that the page is brought to the memory. Okay, so what is virtual memory is, you know, it is an imaginary memory. Okay, how it is beneficial? Because as we are assuming there is the whole program, CPU is able to generate addresses to this particular virtual memory. Okay, and hence, and there is the memory management unit, MMU, which maps the addresses and finds the location in the primary memory. So because of this arrangement of this particular illusion and the CPU generating addresses to this particular virtual memory, okay, we are able to bring multiple programs. There is enough space in the primary memory, and the address and the required instruction can also be accessed. Okay, because there is memory management unit which sees that the required instructions are accessed. Okay, the required address of the physical memory is accessed. Okay, so there is the virtual memory benefit. CPU is able to generate addresses to this physical, the virtual memory. Okay, and however, whatever the address is of that particular program, there is MMU which translates the address, logical address to physical address. Okay, as this translation is done, there is no problem even if the whole program is not there in RAM. Okay, because there is the whole program which is assumed to be here. As this translation is done, we need not worry about the retrieving of the required instruction. Okay, and as the whole program is assumed to be here, there is no problem with CPU for generation of addresses. Okay, only the small part which is required can be placed here. In primary memory, only the required pages can be placed, and hence there more programs can be placed, and hence CPU utilization is increased, utilized more. Okay, and hence throughput is more. Okay, so this is in brief about the virtual memory and its benefit. We will see in detail how it is. Okay, so what is virtual memory? Separate logical memory that is assumed to exist. Okay, as data is stored in main memory, means the secondary memory. Okay, main storage is secondary memory. So as data exists in secondary memory, that is continuously, the program is assumed to be there in virtual memory. Okay, and complete program is assumed to be present in virtual memory. Okay, so creates an illusion of very large memory which is not there. Okay, actually not there. Benefits: only part of the program needs to be in memory for execution. The whole program need not be there in primary memory. Okay, how is this possible? How you are keeping only part of the program? Because we are assuming that the whole program is stored in virtual memory, and addresses are also generated by CPU for the complete program. Okay, but actually how much we are storing? Only the required part. Only the required part of the program is stored. Okay, much larger than the primary memory. This virtual memory is, okay, allows memory to be used for storing several programs, which improves the CPU utilization and hence increases, several programs are there, it increases the degree of multi-programming. How does it, what is the advantage of increasing the degree of multi-programming? There is higher CPU utilization, more programs are there in memory. So even if the programs are waiting, the other programs can be given for CPU to execute. Okay, degree of multi-programming is increased, and CPU is utilized well, throughput is increased. Okay. Virtual memory can be implemented with the help of something called as demand paging. Again, the concept, what you assume to be demand paging, we'll discuss about it. What is demand paging? Okay, so now, as of now, any doubts which you are getting? Any doubts? Okay. Now, we have seen a similar diagram in the previous module also. So here, this is the virtual memory. Complete programs from page 0 to page V is assumed to be stored. That is actually present in the secondary memory. Okay. And there is memory mapping unit or memory management unit. In paging concept, it is the page table, which maps the addresses. Page table in paging concept. Okay, the address which is generated by CPU to this virtual memory is converted to physical address by the memory management unit. Okay, and if suppose this page is not there, the swapping is done, you access the page from the secondary memory and it is stored in any of the free frames in the primary memory. Okay, here this is swapping which is taking place here. Okay, we'll see that in detail about the swapping and how this is being accessed here. Okay, what is that access? We'll see it. So this shows that here virtual memory is much larger than the physical memory. Physical memory, suppose it is of 512 bytes. The virtual memory is the size of the complete program. How much ever the program size is, that is the size of the virtual memory. Okay. So demand paging, I had told that virtual memory is implemented and it is possible, virtual memory is possible because of demand paging. What is demand paging is? I had told the word demand paging in the previous module itself. So what it is on demand, the page is accessed from secondary memory. Okay, that's all. So all the pages are not there in primary memory initially. On demand, the page is accessed from the secondary memory. Okay, so that is demand paging. So I think it is, you all of you can assume what it is. So secondary memory programs are here. Okay, so pages are there in secondary memory, and if suppose the required page of a program, so P1 programs page 0 is here, P1 programs page 1 is here, and page, okay, so P1 program has 4 pages, suppose page 0, page 1, page 2 and page 3. This is the virtual memory. Okay, and CPU wants to access now the second page. Second page is required, so it generates a logical address page 2, an offset of 3. Okay, now it wants to access page 2. Page 2 is not there in page table where there is page numbers and frame numbers. Okay, page 2, there is no data. When there is no data, that means page 2 is not there in this physical memory. Okay, so when it is not there, page is to be accessed from the secondary memory and stored in one of the free frame. So if any frame is free, the data has to be stored there. The required page has to be stored there. Okay, so this is demand paging. On demand of the processor, the page is accessed from the secondary memory. Okay, so that is demand paging. Bring a page into memory only when it is needed. Okay, less IO needed. So whenever the program starts, P1 program starts, all pages are not brought to the memory. Okay, only a required page is brought to the memory. So less access of the secondary memory. Okay, so access of the secondary device, you are reading the data. Okay, so reading input from the secondary memory to the primary memory is reduced, less needed, because only required page is accessed, only required page. Okay, so less input from the secondary memory. Less memory needed. Yes, I'm not using the storing all the pages, so it is less memory which is needed. Faster response of the system because more memory is free. Okay, and more user programs can be stored because of demand paging. So if a page is needed, use it if it is there in the primary memory. If the page is not in memory, bring it to memory from the secondary memory. Okay, so this is the concept of demand paging. There is a diagram which indicates the demand paging concept. Okay, so this is the diagram which indicates the demand paging concept. So we'll see in detail what it is. Okay, so all of you have understood what is demand paging. If the required page which has to be read, which has to be referred by the processor is not there, that page is brought from the secondary memory to primary memory. Okay, page 2 is required of program 1, page 2 is not there. So it is there in secondary memory, bring that page from secondary memory. That is demand paging. If needed page is there, use it, refer to that page of which is present in primary memory. If page is not present in memory, bring that page to the memory. Okay, so when you are bringing the page to the memory, swapping can be done. Okay, so here in disk, if it is shown like this, I have told it is a secondary memory. Okay, so these are the small blocks in the disk. You have seen the disk structure in the PCD. Okay, second sem itself. You have seen that there is the secondary memory. Number of disks are there, arranged one below the other. Number of disks are there. All those disks are the programs are stored in this tracks like this. Okay, so there is a disk, uppermost disk. There are tracks. The disk is divided into number of tracks. Okay, so in this tracks, when you see the CD also, you can see the tracks where the program is stored. Okay, so these tracks are divided into number of sectors. This is one sector. Okay, so this is one sector. The tracks are divided into sectors. This is a part of the track. Okay, this is a part of a track. These are sectors. Okay, so here addresses are done to the sectors. Address are given to the sectors. Okay, means if I say in secondary memory, track 3, okay, in track 3, sector number 12, so like that. Okay, so addressing is done to this sector, and sector is the basic data base at a time when the data is read from memory. Okay, from secondary memory, one sector of data is read. Okay, now coming to this block, I just want to tell what does diagram represent. So here one square means it is block of or a group of sectors. A group of sector is represented here in block. Okay, so data is stored here continuously or discontinuously depending on the arrangement architecture of the disk secondary memory. The data will be stored. We will see in the file management how the data are stored in secondary memory. Okay, now suppose a file is continuously stored. Okay, so the program can be swapped out and the program is swapped in. For if sufficient space is not there in primary memory, swapping out and swapping in is the concept. You have seen that. Now you have also seen about the valid invalid bit in the previous module. What is that valid bit is? It indicates that the page is valid in the page table. Okay, so every page table will have a valid invalid bit along with the frame numbers. Okay, there is page number, which is the index. Okay, and frame number indicates in which frame number of primary memory. So frame number 5. So frame number 5, page 0 is present. That is the indication. Now when I put it is valid, V means it is valid, means valid page 0 is present in frame number 5. Okay, the valid page 0 present in frame 5 is valid, means updated. Okay, or correct data is present in the memory. Okay, if suppose it is I invalid, means the page, the data what is there in, if suppose there is frame number, okay, so since it is not valid or it is not updated data, some other data is there. Okay, so content is not valid. Okay, content is not valid means in memory, in frame number 6, whatever junk data is there, some data is there, it is not correct data. It is invalid data. Fine. And that should not be accessed. So depending upon the page table, valid, invalid bit, the operating system will come to know whether the particular data in the particular frame is valid or invalid, or the particular page which is required is present or no. This page is present or no in memory. Okay, is understood by valid invalid bit. Okay, in short, what I can say is in page table, if the data what is present is V, it means it is a valid page and the particular page, okay, in the particular frame can be accessed for retrieving the instruction. Okay, if the value is I, means the data is not valid in that particular frame. Okay, so it is set by 0, valid invalid bit set to 0, or I, it is indicates that it is invalid data. Okay. So if it is invalid data, means that page is not loaded into the memory. Just you can observe this diagram correctly. So this is a program P1. It contains 8 pages. Okay, some data I have put some data. Okay, ABCD. So 8 pages it contains. You can see the secondary memory where the 8 pages are stored. Okay, 8 pages are stored here. Now, are all the 8 pages present in primary memory? No, all 8 pages are not currently required, and hence it is not stored in secondary memory, primary memory. Okay, only page A, that is content A of page 0. This is page 0. Okay, and page 2 content is there, and then page 5 content is there. Page 5 content is there. You can see the page table also. Page 0 is in frame 4, yes, and it is valid. Page 2 is in frame 6 and it is valid. Page 5 is in frame 9 and it is valid. Okay. All other pages are invalid. Means what? Bereyav page, no other page is brought to the memory, primary memory. Okay. So no other page is brought to the primary memory. Right. Now, suppose the processor generates logical address. It wants to access the instruction C. Okay, C is there. Page 2 is already there. Okay. It wants to access the instruction D. Okay. So it produces the address page 3 and then offset of some in that page. Which instruction I want? I want the second instruction, suppose. Okay, so page 3, check in the page table. As soon as the address is generated, this has to be converted to the physical address, correct? So this logical address, check the page number in the page table, page 3, it is invalid. What does it indicate? Page 3 is not present in the primary memory. Okay, page 3 is not present in the primary memory. Where can I get the data from? Where can the operating system get the data of page 3? It is there in this secondary memory. Okay, it has to get, the operating system has to get the data from secondary memory. It is not here. The page 3 content, that is D, is not here in the primary memory. Okay, so this is how, by using the valid invalid bit, you can know that whether the updated data or the data is present in the primary memory. Okay, any doubts, students? We'll see about the demand paging next. Now, before that, I just want to tell that there is, in page table, there is a valid invalid bit which indicates whether the required page is present in the physical memory or the primary memory or no. Okay, so there is a bit which indicates the existence of a particular page. And if the page is not present, I want to access page 3. Page 3 is set to I, means that page is not present in the physical memory. If the page is not present, if the required page, okay, required page is not present in physical memory, then it is called as page fault. Okay, it is called as page fault. Very important term. It is, we say that a page fault occurs, or page fault has occurred when the required page is not in physical memory. How does the operating system know it is a page fault? By using the page table. Okay. So page fault is, okay, if there is a reference to the page table and the required page is not present in memory, it is said as a page fault or invalid. It is an invalid reference. The CPU's address is means it is not able to access that reference. Okay, so it is a page fault. Whenever page fault occurs, the required page is not in memory, and search for an empty frame in the primary memory and store the required page there. Okay, that is how the demand paging works, okay, or the page fault is handled, handling of page fault, or on demand, how the page is brought to memory. These are the steps where how the page is brought to the memory on demand, okay, or handling of page fault. Very important question. How the page fault is handled. There are 6 steps. Okay, CPU is generating an address and it reference the page table. Valid invalid bit is set to I. A TRAPS, a signal is sent to operating system, indicates that a page is required which is not in the primary memory. Okay, operating system searches in the secondary memory where the page is present, checks the address where the page is present, go and access that memory, checks where is the free frame in the primary memory, and stores this page into this free frame. Once the data is loaded, suppose it is the frame number 7 where the page is loaded, okay, the data is updated in the page table. So page 3 is stored in frame 7 and this I is set to V. It is set to a valid bit. Okay, and restart the instruction. Okay, and this is how page fault is handled. Okay, simple, when I say in simple terms, that page is required, page is not there, it is brought from secondary memory to the primary memory. Okay, when it is brought to the primary memory, the frame number wherever the page is stored, it has to be updated in the page table, and that is happening here. It is updated, frame 7 is updated, and I, the invalid bit, is set to valid.